So we've talked a little bit about hypothesis testing in the previous module, and there will be more hypothesis testing considerations in the coming modules that are in this course. But basically the idea behind hypothesis testing is that you start out with the assumption that there is no difference or no relationship between two variables, and you check to see using statistical testing whether you have evidence to reject that hypothesis and conclude that there is a significant difference. So that's the basic idea behind hypothesis testing, and related to that is statistical power. So I want to give you a brief overview of statistical power, primarily so that you know what it is and how it relates to hypothesis testing, but also because for some of you this may be a useful topic to think about as you make plans to do your practice inquiry project. And I should also underscore that if your practice inquiry project will involve data collection, including chart review or other types of data collection, I will be happy to assist you with planning your study and deciding how many subjects or charts you need to include in it. But just to give you an idea of what this is, I will be talking about the specifics of power analysis, including type 1 and type 2 error, and so on. So I'm just going to skip to the next page. So in the context of hypothesis testing, alpha is the probability that you reject the null when it's actually true. So I'm going to just start as an example the idea of having a test of the difference of two means. So my just very generic example is going to be whether, for instance, men and women differ on height. So that's a pretty boring hypothesis to test, but let's just say that we have a population, say perhaps of all the students who attend UK. We have a population, and from that we're going to choose a sample to decide whether there's evidence to suggest that the heights of men and women are different. So in that context, alpha would be the probability of rejecting the null hypothesis and concluding that there is a gender difference when in fact there is not a difference. That if we were able to survey the entire population of UK students, we would find that on average males and females have the same height. So alpha would be the probability of rejecting the null based on our sample when in fact the population does not have a significant difference between males and females. Also in that same context, the other type of error is beta, which is the probability of failing to reject the null when it's actually false. So if in fact in our population of students at UK, there is a difference between men and women in terms of height, but the sample that we take and the hypothesis test that we run shows that there's not a difference, that would be a beta or type 2 error. So then power is related. So again, circling back to what the original premise of this handout is about. Statistical power is really 1 minus beta. So it's the probability of rejecting the null when it's actually false, when in fact you actually should. So in the context of our example, that would be, power would be the ability of our sample to demonstrate that the average height between men and women is significantly different. So there's a trade-off between alpha and beta. It's impossible to increase one without decreasing the other. So we can't increase the power without also increasing the type 1 error rate. And I'll just give you a little background example of that. If for example, we decided that a type 2 error, a beta error, was the type of error that we just would not want to make no matter what, then the only way that we can be positive that we're not making a type 2 error is, which again is failing to reject the null when in fact we should, would be if we always reject the null. We always reject the null. There's in fact no reason to even collect data or take a sample, because we go into it thinking, if I don't want to make a type 2 error, my only way of avoiding that, of making beta equal to 0, is if I reject the null no matter what. But if I reject the null no matter what, I will always reject the null even when I shouldn't, which would make my alpha, or the probability of rejecting the null when it's actually true, equal to 1, or 100%. So it would go the same way. If I wanted to make alpha as small as possible, I can only do that by increasing beta. So what has happened practically is that statisticians sort of have developed this rule of thumb where they've said, we've decided that acceptable levels of error for alpha and beta would be 0.05 for alpha and usually 0.1 or 0.2 for beta. It sort of depends on the context. So what does that mean? That 0.05 is probably a familiar value to you, like maybe from your prerequisite statistics course, and that's saying that when we run a statistical test and we find out that the alpha level, that the p-value is less than 0.05, our conclusion is that we would reject the null and conclude that there's a significant difference, for example, between the heights of men and women. So that 0.05, the reason that that's used as a cutoff or a guide for what would stipulate a significant p-value is because that is the alpha level that has been set for that test. The beta level set at 0.1 or 0.2 is usually set that way because we want to have power that's 80 to 90%. So since beta is related to power, since power is 1 minus beta, having a beta of 0.1 or 0.2 would be equivalent to having power of 0.8 or 0.9. So that's a little bit of background about that. And then let me just, this is kind of this table, I added it actually. If you've already printed off the power analysis handout from when I first posted it, this wasn't in there, but I thought this would be helpful to look at, just as a way of talking about the different types of possibilities. So again, I'm just referring back to the example of men's and women's heights. So it just as a simple example of illustrating this, but whenever we have a hypothesis testing situation like that, there are always two things to consider. One is what's actually true in the population. So the two possible things that could be true is that the means are actually different. The mean heights of men and women are actually different. Or the other possibility would be that the means do not differ from each other. And so we won't ever actually know which of those two things is true because every time we talk about doing hypothesis testing, it's always within the context of a sample, which is just a subset of the population. But one of those things is true, regardless of whether we know them or not. And so that is what we're trying to, we're trying to get at what's the most likely of those two things to be true, given what we know from a hypothesis test. So if you look at the first column of this table, the hypothesis test also has two possible outcomes. One would be that you reject the null hypothesis and conclude that the means are different, or that you fail to reject and conclude that there's not enough evidence to suggest that they're different. So, given the two possible true states of being and the two possible hypothesis test outcomes, there are actually 4 combinations of these two things. And for 2 of those combinations, you actually arrive at the correct conclusion. And one would be, if in the population the means are actually different and you are able to show that with your hypothesis test, then the conclusion fits the reality and the means are different. So this would be no error. This is neither a type 1 nor a type 2 error. This would be a correct conclusion. The flip side of that would be if the means are actually not different from each other and you fail to reject the null hypothesis, you get a p-value for that comparison of means that's large. And so you do not reject the null. You say that p is greater than 0.05, so I conclude that there's no difference between the means. That conclusion fits with the reality that in the population, the means do not differ from each other. So we only really care about, when we're talking about type 1 and type 2 error, we only really care about the other 2 scenarios, and that would be if in the population the means are not different from each other, but based on our sample, we reject the null hypothesis and conclude that they're different. That would be the type 1 error, or alpha, that I talked about on the previous page. On the other hand, if the means are actually different, and we fail to reject the null hypothesis, our t-test suggests that p-value is large. We failed to reject the null hypothesis. So our conclusion would be that there's not enough evidence to suggest that the means are different, even though in fact they really are. This would mean that we have a type 2 error. Again, we won't know when we're committing either type 1 or type 2 error, but we try to set the alpha and the beta at such a level that the likelihood of making that type of an error is small. I have, to try to make this a little bit more concrete, I have several examples of how differing levels of alpha level, sample size, and variability influence statistical power. So this first one, what this actually is there are sets of curves, two sets of curves that show where the rejection region is under the null hypothesis of no difference versus the alternative that there is a difference. So this example is actually the effectiveness of a diuretic. And so two patient groups were given the diuretic or a placebo. Nobody knew which kind of drug they received, and it was a comparison of urine output between the two groups. So at the top two curves, what that shows actually is the distribution of possible t-values. Again, since it's a comparison of two means, we would use a two-sample t-test to compare them. So it's the distribution of all the possible t-values that you might get if in fact the diuretic was totally ineffective and it didn't influence urine output at all. So if that were true and you had a critical value of 2.101, that would mean that anytime you observed a t-value that was greater than 2.101 or less than minus 2.101, you would reject the null hypothesis and conclude that the means were different. So what the shaded value for that very top figure is 5% of all the possible t-values are within those two tails, so 2.5% in either tail. Now, if instead of, if the true effect of the diuretic was to increase urine production by 200 mils a day, then we would expect that on average, the patients who are randomized to get the active drug would have a value that was 200 mils higher than the other group, and the possible t-values as a result of that shift would be 55% of the possible t-values would be higher than 2.101. So 55% of the time, we would reject the null hypothesis and conclude that the two groups were different, that the diuretic did have an effect. And we contrast this to the other situation where, let's say we decide that our type 1 error rate, we want it to be smaller than 0.05, so we decrease it to 0.01. This puts 1% of the possible observed t values in the two tails for the distribution. So under the null hypothesis, you have a higher critical value for t. So now instead of looking for a t that's greater than 2.1 to indicate significance, you would look for a t value that's greater than 2.4 by rounding. And so if I see a value that's greater than 2.4, then I would conclude that the groups are different. But raising that critical value to 2.4 decreases the number of, or the percent of time that you will have a t value that's outside of that critical value of 2.379. So even though you still have the effect of 200 mils per day increase in urine production, you would reject the null hypothesis only 45% of the time. And this agrees with the observation that we had originally, that if I decrease alpha, I necessarily increase beta or decrease power. Because I make it, by decreasing alpha, I'm making it more difficult to reject the null hypothesis in general, which also is more likely to lead me to a type 2 error or diminished power.